Okay, well, welcome back and good morning. So I'm just starting here with a little pretty picture of magnetic nanopillars that are undergoing switching. Simulation, of course. So let's get down to business here and let's show on the road. Okay. Yeah, so I'm going to continue, and at the beginning, actually, I'll be repeating some of my stuff from yesterday. So I am looking at magnetization switching very much from the point of view of a statistical mechanician and someone who's interested in metastability and its modes of decay. And as you can see, this is work that's been done with a lot of collaborators over like a 15-year period or something like that. The main people I should mention is Mark Novotny, is now the head of the physics department at Mississippi State. Greg Brown, who's been with us for a long time, he now works for a research company in Tallahassee, but still works with us. And so, now, you could always ask, of course, why is this interesting? At least one has to convince someone, like the people with money, that it is. So, from an applied point of view, really these anisotropic magnetic nanoparticles are really hot materials for ultra-high density magnetic recording media, and of course that's something we are really into. We all carry around laptops that have hard drives that are hugely bigger than the hard drives of a few years ago. The other, from a scientific point of view also, is that it's really not that long that we have had the means to observe these systems on a microscopic scale. That really depends on force microscope, like magnetic force microscopy, atomic force microscopy, scanning tunnel microscopy, and so on. And these techniques really only go back 20, 25 years. So, for this reason, really, switching behavior is both a technologically important question, and that of course means that there's actually some money to be had in it, and it's an interesting problem in non-equilibrium statistical mechanics because it has to do with the modes of decay of metastable phases. So that was the motivation. Now this is an old slide, and I haven't really been able to find a new and prettier one. So it's actually now almost 10 years old, but it's a plot of storage density in gigabytes per square inch as a function of time. And this line is lab demonstrations. This other one is volume shipment. So essentially what you're seeing here is something that's for storage the same way pretty much as Moore's law is for CPU power, namely an exponential increase. And so I've also extrapolated along. Now there's also here a horizontal line, and that's luckily that horizontal line actually keeps creeping upwards, and that's what's known as the superparamagnetic limit. And so essentially what we're saying is that if the storage density gets very high, that means we'll have to store our bits on very small particles, and at some point then we get to where thermal fluctuations are important. And Now the trick now is to find ways of storing the information in such a way that on the one hand we can write it with reasonable field strengths and at a reasonable speed. On the other hand, the information shouldn't decay quite too soon. I mean, we like to be able to write fast, and we want our hard disks to keep information for years. And those are actually, if not mutually exclusive, they take some thinking and some experimenting to try to optimize in between. We also, of course, don't want to have to carry our laptops around in a vat of liquid helium, which would sort of negate the advantages of miniaturization quite a bit. So, therefore, as the industry has become aware of this and become aware that this problem actually involves a good bit of statistical mechanics, they've become much more interested than they were, say, 15 years ago when we started preaching this stuff. So here's one way of looking then at the superparamagnetic limit. So here, this is actually now pretty old data, 1993. So we're looking at the switching field, and I will define switching field a bit more carefully later on, but right now let's just say that I set some time scale, and I say that the switching field, say I have a magnetic particle that's magnetized in one direction, I apply a field in the opposite direction, and I say what's the field such that with probability 1/2 or half of my ensemble of magnets will have flipped within that time, and I call that the switching field. And here what I'm seeing is the switching field for barium ferrite particles as a function of the particle diameter. And essentially what we see is that as I lower the diameter from large values, the switching field tends to increase, but then as the particle gets too small, the switching field will decrease quite precipitously again. So these are experimental data, pretty old by now, and these are simulation data from two-dimensional kinetic easing models, and I'll show you this type of plot again later on in the talk, where after I've related them to some of the stuff I talked about yesterday. So right now, this is a teaser which says that yes, I can use a kinetic easing model to get qualitatively the same sort of behavior of the switching field versus system size as you see in experiments on nanoparticles.
Question?
Yes?
For data storage, do you want the switching field to be big or small?
It's actually, I want it both ways, as usual. In order to write quickly and reliably, you want it not to be too strong. On the other hand, for your information to be held reliably once it is written, you actually want it to be large. Yes?
Can I just
yes.
I think that's right. You want the switching field to be low, but you want the energy barrier to be high. That's another way to say it.
Yeah.
I think, which are not necessarily incompatible.
That's true. So, and there are lots of tricky ways to go about this, like, for instance, to heat as you write, because you can lower the barrier, or you can increase the probability of going over the barrier by heating and so on. So, yes, but a lot of the problems with pushing the superparamagnetic limit are problems of somehow getting it both ways. Okay, so let me show you some pretty pictures. So this is then an example of a potential recording medium, and the latter half of this talk, I'm actually going to show you simulations of computational models of this. So these are iron nanopillars produced by Avshalom and Steve von Molnar, who is actually at Florida State. And so here we see an atomic force microscope picture of such iron pillars. So these are about 40 by 40 by 200 nanometers. And they are sitting, as you can see here, actually they're sitting on top of a Hall cross that can be used to measure the magnetization. And these days also they are able to put a single such particle on the cross. So, in other words, I have these long, thin nanoparticles, something like this, and here then I'm showing to the left and to the right, I'm showing magnetic force microscopy images. So that's another scanning microscope technique that allows you to see the direction of the local magnetization. And here, on the left, I have it with random magnetization. So say the white ends are south poles and the black ends are north poles, or the other way around. And so you see, here's roughly equal numbers of volts, so it's a random magnetization. On the right-hand side, we see that by applying a field, in this case 200 Gauss, we can align this whole array with the field. So, again, I say I will get back to these particular systems later on. I just want to show them to you. Then I want to try to dispel some confusion that is very hard to dispel, I found out. And that is, I will try to make you distinguish between domains and droplets. Now, domains are an effect of the magnetostatic interactions, and it's basically a way of reducing the equilibrium free energy of the system. So, for instance, Andy already showed us pictures of these where you get these closing behaviors. So I can get a domain here that points that way, a domain here that points that way, and then at the end something like this that will essentially reduce the magnetic field outside the particle, and so reduce the magnetostatic energy. Now, this is basically an equilibrium case. Now, what I'm going to be interested in are particles that are small enough that in equilibrium they are basically single domain. So they won't break up in equilibrium. But as I told you last time, even if I have a system that is single domain in equilibrium, like last time I talked exclusively about Ising models with nearest neighbor interactions. They have no magnetostatic interaction. They have no tendency to break up into multi-domains in equilibrium. But nevertheless, the switching behavior, as we saw in the short-range model, is dominated by local temporary fluctuations that I'll call droplets. So in this case then, what I have here is a picture where the background here is magnetized opposite to the applied field, so it's in the metastable state. This droplet here is magnetized parallel to the applied field, so that is actually in the thermodynamically stable state. And in this case then, I have shown a supercritical droplet that would tend to grow with time. if the droplet, as I showed you last time, is too small, then it is subcritical, and it will tend to decay back to the metastable background. And here actually someone after my talk yesterday pointed out to me that I'm really using the word decay here in two very different meanings. When I say that the fluctuation decays, I mean it goes back to the metastable base. So say I have all spins up, field is down, one single spin flips. Now it will be in disagreement, it will be antiparallel to all its neighbors. If the field is small enough, the gain in energy by flipping parallel to the field is less than the loss, than the increase in energy by being opposite to all your neighbors, and therefore this single flipped spin will tend to flip back. That's what I meant by a subcritical fluctuation decaying back to the metastable background. On the other hand, I also used the term metastable decay, where I mean the decay of the metastable phase to the thermodynamic equilibrium. So, pardon me for this somewhat confusing use of terms. So in this, but hopefully that's now clarified a little bit. So just then what I want to use, well, I'm going to start again with the kinetic easing models that I talked about yesterday, and I'm going to give you just a quick review of some of the stuff I said then, and about the nucleation theory, and then I'll then pull that on till I can show you these non-monotonic switching field behaviors, and show that it's essentially a direct consequence of the switching of the lifetime versus field curves that I showed you last time. And then I will switch gears and I will start talking about models of these magnetic nanopillars and using the Landau-Lifshitz-Gilbert equation that you were already, that Andy already introduced you to yesterday. So, okay, this slide you've seen before. It's my kinetic easing model, and so we can spend very little time on it. Again, if the feed, so we're below the critical temperature, so therefore the spins will like to be aligned. Without an applied field, the two aligned directions are degenerate. Apply a field, then the direction parallel to the field is going to be the stable, the thermodynamic stable state, and the other one is going to be metastable. And I also showed you that if I have a system where the interactions are local, and that's really what governs the criticality, even in magnetic systems. I will add the complication of the long-range magnetostatic interactions later, but in terms of the nature of the metastability here, that's really given by the short-range interaction. So, therefore, we have these local fluctuations. Okay, once again, I'm going to use the simplest stochastic dynamics. I'll be using either Metropolis or Glauber. And so here now is my metastable phase diagram that I showed you last time. So remember, that was a result of the fact that I essentially had 4 length scales in my problem. The smallest length scale is the lattice constant. Then comes the critical, the RC here, which is the average distance between droplets. And then I have, that's RC, so sorry, I don't have my glasses on, so I don't see my own slides. Okay, this is RC. So I said right, but it's not this is the I said wrong. It's the critical droplet size. So that's the size of a critical droplet. If the droplet is smaller than that, it decays back to the metastable background. If it is larger than that, it will tend to grow and increase the volume of stable phase. Here's R0. That is the length scale I obtained from the Avrami theory and the fact that the droplets grow at a finite rate. And I showed you that that's essentially the distance between droplets. And so the question is then, how does L stack up against these three? So there's the three intrinsic length scales, if you like. And then I have the system size, and I've got to ask, how does that stack up with respect to these? Well, the single droplet regime is essentially when the L is less than the difference between the distance between droplets, but bigger than the critical size. So that means I have that's what we call the single droplet regime. It is the most probable now that the system will go from the metastable state to the stable state by way of a single droplet that nucleates and then grows to take over the system on a time that is short compared to the time you would expect to wait before another droplet nucleating somewhere else in the system. So single droplet domain. And then multi-droplet domain, I say, is when the system is much larger than the average distance between droplets. In that case, droplets all over the system will nucleate and grow while droplets elsewhere in the system already are growing. So that's the multi-droplet. Then I can take the crossover, the field strength, where we cross over between those two regions, and that's what I will call the dynamic spin-oval. So it's not a critical line like it is in long-range models, it's a crossover. And as we also showed last time, this crossover, if the system size goes to infinity, it goes to 0, but it does so logarithmically, which means that in terms of metastability, the infinite system limit, or if you like, the thermodynamic limit, could be microscopic. And we have lots of examples of that. One example was, of course, Fahrenheit's little evacuated glass bulbs with water, which certainly you'd think a liter of water is macroscopic. Well, in the sense of decay of the metastable supercooled fluid state to the solid stable ice state, it is actually not anywhere near the thermodynamic limit. So then inside here is single droplet, multi-droplet here, and then if L becomes smaller than the critical radius itself, then essentially a subcritical fluctuation is enough to switch the system. And that's what we call the strong field regime. So this line then, what we call sometimes the mean field spin-oval, although it's not really mean field, that is independent of system size. The dynamic spin-oval is dependent on system size, but only logarithmically. And then in this curve, I actually didn't even show. There's another crossover here, where the critical radius becomes on the size of the lattice constant. And then the system is, it becomes other way. When L becomes smaller than, L becomes smaller than the critical droplet size, then essentially a subcritical fluctuation can flip the system. So here, every fluctuation is supercritical. Here you have a number of supercritical fluctuations. Here you have a single supercritical fluctuations. And here, even a subcritical fluctuation can flip the system. So here, now let's go back. Again, you have seen these before. Here I use the fact that the lifetime went as an exponential function of 1 over field to the d minus 1, where d is the dimension. I could plot, if I plotted log of the lifetime versus 1 over field in 2 dimensions, or 1 over field squared in 3 dimensions, then I can see the crossover between single and multi-droplet decay in this way. And we may remember from last time then that at this crossover, the slope with respect to 1 over field to the d minus 1 is going to go from a particular value to that particular value divided by d plus 1. So in 2 dimensions, this slope will go from something to 1/3 of that. And for a small system, this crossover happens at a larger field than it does for a bigger system. Right? This is still just repeat of last time. Now, let's go back and talk about the switching field. So now, let's concentrate first on this bottom slide, where I have, for some reason, we never really did a full simulation study for 2 different systems going all the way up here. So I have, this is an old one from a review article I wrote back in 1994. But so here are simulation results. The dynamic spinodal, you see, for a smaller system sits here. This is a 128 by 128 system. For a larger system, 720, it sits here. Now, for the smaller system, I come to this point here where the system becomes smaller than the critical droplet. And then, essentially, the lifetime becomes very weakly, or essentially independent of the field, if I make the field even smaller. For the larger system, it's here in the single droplet regime. As you may remember, the lifetime is inversely proportional to the volume of the system, and therefore the lifetime becomes smaller as I make the system larger. But the crossover to the very weak field region comes at a much smaller field, and therefore the 2 lines actually cross here. So now let's take a system. So say here now, I choose a time, and right now let's choose the time here. Then, for the small system, the lifetime, the switching field, its inverse is very large, so the switching field is very small. Right? But then increase the system size, and I move from this very weak field regime into the single droplet regime. Right? So now we're looking at this So now the field has gone from very small to some relatively substantial value. And then if I make the system much smaller again, I could get to where this time actually corresponds to the multi-droplet domain. So that's then what we see here. So now essentially what I do instead of here, I keep the system size constant and vary the field and measure the time. So this line here is a function, time as a function of field for constant system size. Now we'll turn this around, and in these plots I'm instead going to fix the time, as I said, here, and as what's the switching field, defined now as the field such that the probability of the system switching within the given time is 1/2. And now I'm going to vary the system size. Here, this peak essentially corresponds to what I call the thermodynamic spin-over, the point where the system size becomes of the order of the critical droplet. Below, if it's smaller than that, the system is very easy to flip, because I only need some essentially statistically uniform. And therefore, I would say I would identify the superparamagnetic limit with this line. And then, out here is the dynamic spin oval. So, in other words, as I increase the system size, the switching field is very weak. It increases, goes through a maximum where the system is on the order of the critical droplet in size. Then we cross into the single droplet decay regime. And that, as the system becomes larger, the nucleation probability becomes larger, and therefore it becomes easier to switch, and I need a weaker field until I get into the multi-droplet regime, where the lifetime is independent of the system size, and then this will essentially plateau out. So this is just the same data as this, plotted in a different way. And so here then, we've shown 2D and 3D. So the other thing we see here then is that as I change the waiting time, as I increase the waiting time, the switching field becomes weaker, as you would also expect. And here's then 3D cubic. Now, I must admit that of course this is a little bit hokey, because these are periodic boundary condition results. And yes?
Explain again, why is it that the field, the critical field increases when you increase the system, the size?
Okay, yeah. Let's try again. Let me see if I can get up close and personal here with the graph. So, okay, let me fix my time here. Right? So you see now for this very small system, see this is 128, right? For this small system, the time I chose is longer than the lifetime of the system, even in very weak fields. So therefore, essentially, on this time scale, the system will switch even for extremely weak field. Remember, this direction is weak field. Large inverse field. Now, if I make the system bigger, then essentially this, I'll get a smaller, I'll get a straight line at a lower value, but that straight line will continue up quite far, maybe up here before it bends over. And therefore, now, at this point, now for this size system, 50% of the spin of the systems would flip for this time. So now, instead of being at a very weak field out here, I am now at some relatively stronger field. But then, as I make the system even bigger, we're now in the single droplet regime. As I increase the system size, this is inversely proportional to the volume of the system. So this line now comes down and therefore moves back. The switching field becomes weaker again. And so essentially, where this almost horizontal part of the curve crosses my fixed waiting time is where the switching field will see its maximum. Below that system size, the switching field will be weak, the system will be thermally unstable. About for larger systems, it's going to come down again. If the system becomes so large that we get into the single droplet regime, you see, then the lifetime becomes independent of system size, and therefore on this sort of plot, I will get this will become horizontal. Yes.
What do you mean, if you increase the system size, it should go to a multi-droplet regime? What do you mean it goes into a single droplet?
It first goes. So this is the regime where the system cannot even accommodate a single critical droplet. So it's a subcritical droplet. It doesn't need to make a full critical droplet in order to. So then I get. So after that, this crossover line, this in terms of field, it goes as 1 over field. So I go from that regime, the very weak field regime, to the single droplet regime, and then to the multi-droplet regime. And what I should do to make this pedagogical, I really should do 3 different system sizes all the way. We should go back and do that. So as I increase the system size from very small, I first go through a regime where the system is much smaller than the critical droplet. Then it gets bigger, so it gets harder to flip it, until I get to here. Then I get, now my fluctuations are suddenly local, because the system is now bigger than the critical droplet. So then I will be in the single droplet regime, and then I'm crossing over into the multi-droplet regime.
So why does it decrease in the single droplet?
It decreases in the single droplet regime because in the single droplet regime, as I increase the system size, the probability of nucleating a droplet increases. Because I have a constant nucleation rate per unit volume. So that's this part of the curve. Is this getting reasonably clear? Okay, yeah, but I really should produce some better graphics for this point, I can see. All right, so a few bells and whistles. I see I really shouldn't spend too much time here because I have more stuff to show. I just wanted to show that even if I relax my very idealistic conditions of periodic boundary conditions, no impurities, and so on, then the system, the things don't change too much. So here I put on some different boundary conditions, and you see, yes, this peak becomes less pronounced if I put on somewhat more realistic boundary conditions, but it doesn't go away completely, at least in many cases. And in any case, I do have this fall off for very small systems. We've also experimented a little bit with different amounts of bond disorder, and what we again found was that the shape of the switching field curve doesn't change all that much, at least for modest. And this is really just preliminary results. We worked a little with it, but we have not systematically worked with impurities. Okay, this is sort of just something a little bit of an entertainment because I have a nice movie here. So this is what is known as a iron sequilayer, and if you don't know what that means, I didn't either when we first did it, but it is sesqui means 1/2, like in sesquicentennial is a 150th anniversary. So this is essentially that I have put on a non-magnetic substrate, I put a monolayer of iron, and on top of that monolayer I put islands at a lower density, the sub-monolayer. And in this case, these are islands, and then I just want to... So this is a pinning type problem, and I'm just going to show you this little movie. So here now, I have this is in the metastable state, this is in the stable state. I have an interface now going across, and I'll just show how this interface will get pinned by these islands and then sort of snap past them. So you see, it hangs, and then when it manages to climb onto an island, then it climbs past it, and this is where it will sit till the end of the movie.
There's some small fluctuations in reverse phase.
Yeah.
This
is
subcritical droplets in the reverse phase.
This is true. Yes, that's what they are. Yes, you've got a sharp eye.
And we also see them on the right.
Yes. You see this. That's the very nice thing with the movies, is that you see the very small subcritical fluctuations very well. Say 1 and 2 spins. All right. All right. So now let me go on to continuum spins. So I'm essentially just going to show you the LLG equation. So even though I spent a lot of time on the first half of the talk, now Andy has helped me because he's already introduced the LLG equation. So essentially then, it's just the magnetization vector. So this is now a 3-dimensional Heisenberg spin at lattice sites, and it's really, it's coarse-grained. It's not the microscope. It's not the atomic resolution here, but So roughly the resolution we're using here is about the same, the length, the exchange length. So in other words, the local magnetization therefore processes around the local magnetic field. And then, as Andy explained, that, of course, would not come to equilibrium, and so we have this phenomenological damping term that will eventually allow the local magnetization to point parallel to the local field. So here's the gyromagnetic ratio. Here's our damping parameter, which in most cases we'll just set at 0.1 without much more ado. Then our local field now has the exchange field, the dipole-dipole interaction, which actually induces a shape anisotropy. Since we're going to be looking at long, thin pillars. We could, in principle, also put in an extra crystalline anisotropy in what I've shown you here. We don't do that. The only anisotropy is due to the dipole-dipole interactions. We have the applied external field, which is just the experimental field you apply, and then we want to do this at finite temperature, so we add thermal noise. So therefore, thermal noise is then related to the temperature and the damping constant by this fluctuation dissipation theorem. So in other words, the correlation function of the thermal field is proportional to temperature, or if you like, the magnitude of this is proportional to the square root of the temperature. This means it's white. Delta function in time means it's essentially white noise, and this just, the mu's are the directions and the i's are the sites, so this is a very simple approximation here, where the thermal effects are local in time, in space, and in direction, XYZ direction. Okay, since we have this random thermal field, this is a Langevin equation, even though the noise term here is hidden in our effective field, the noise part, and that's why, that's so fun with Paris. They have all these streets and squares named after famous French physicists. So here is the one named for Paul Langevin, physicien français, 1872 to 1946. I do not include what? The spatial derivative. Yes, I do. That's it comes through the exchange field, and yes. So this effective field here is a function of the magnetization at the other. So the exchange field essentially is a ferromagnetic interaction between the field, the magnetization at Ri and the magnetization at the nearest neighbor points. So that's where essentially the gradient comes in. So the exchange field is the nearest neighbor interaction between fields, between magnetizations. And then in addition, this also contains the long distance effects due to the dipole-dipole interactions between the magnetization at different points. So that's a long-range effect, and if you compute it naively anyway, it's very expensive.
So this is not necessarily linked to the model. You just hide all the details in the data.
That's correct. No, this is definitely not meaningful.
Question.
Yep.
So H is really not it's not zero mean, right? It's something, and then there's noise on top of it.
Yeah.
Is that how it's doing?
Yes. So this H is then, on the one hand, so this is my spin. Then it contains the directions of all its nearest neighbor spins. And in addition to, and it contains dipole-dipole interactions with the spins all around the system. It contains the applied external field, and it includes the random thermal field. It's all lumped together into that H Gilbert.
And only the random part is, say, zero mean Gaussian or something?
Yeah. Okay. Now, since this is just going to be a very quick advertisement, so dipole-dipole interactions, since that's interactions that extend over the whole system, if I were just going to calculate them naively, that would be an n squared computational problem where n is the total number of spins. Now that's expensive. Luckily, smart people have come up with smart ways of doing this. We are, in particular, are doing what's known as the fast multipole model method. Greengard and company. That is fast. It's actually order n. And there are other methods. There is also Fourier composition, which is n log n. On the other hand, there's more housekeeping with fast multipole, so there's a crossover somewhere where... But anyway, it also has the advantage of handling empty space well, so we can do arrays, and it can be generalized to irregular grids. So now I'm not going to go into details, but it's basically a hierarchical decomposition of the system into, so here's the full system, then I decompose into, say, this, then I decompose into this, and so on. You write the field in terms of spherical harmonics, and off you go. This is as much as I want to say about the multipole moment. So therefore, these long-range interactions now induce shape anisotropy. So I have this long, thin needle. Here I'm showing you 9 by 9 by 150 nanometers on a discretization of about 5,000 lattice points. So I think this is 7 by 7 by 150 by something like that. No, it can't be 150. 9 by 9. Yeah, I think the discretization here is 1 nanometer, not 1 nanometer actually. And so what you see, so therefore, now the magnetization will like to point either along the axis of the particle. And here I am now going to show you a movie of the magnetization switching here. The total length of the movie is 1.2 nanoseconds. And so here, therefore, so here the red is metastable. Then, near the ends here, develop what's known as end caps. End caps are essentially regions where the magnetic field lines sort of splay out in order to minimize the energy. I don't know if you remember, either as students yourself or as TAs in the introductory labs, where you have the lab where the students are asked to trace the field lines of a bar magnet and then extrapolate back and find the poles. And you remember the poles sit just a little bit inside the ends of the bar magnet. This is essentially what's known as pole avoidance, and it's essentially a macroscopic equivalent of these end caps. So now, okay, so what you see now are thermal fluctuations in the end caps. And the nucleation event now is essentially the end cap detaching from the end. And then, in this particular simulation, that it's almost simultaneous at the two ends. That's just essentially, that's random and a relatively rare event. So let me run this once more. So, thermal fluctuations, there she goes. I could also look at the curl. The other thing with the end cap configuration is the field lines splay out. They also tend to lie down in a curl. And so here we see actually the curl is opposite in the two directions, at the two ends. And essentially here you see again, and the curl, as you see, was concentrated on the interface between the metastable and the stable regimes. So they come together, and then they come together in the middle. There's a little bit of confusion here, sorting out the curl, and then you're essentially in the stable state. Okay, here's another. We've just been experimenting with ways of visualizing this. So this is a field line visualization. The coloring tells you the red is metastable, and I'm seeing different views, two side views, end views, and magnified end views of the end. And this is in a field that's parallel to the axis. So there something happens at the upper end, and then the interface just runs down as a one-dimensional driven thing. And only at that point really does the magnetization change much. Oops, that's not what I wanted to do. Okay, now let's see, in the last few minutes here, let's look at switching in an oblique field. So here now I have a situation where, again, I have my pillar, magnetization up. I apply first a field 75 degrees to the axis. I allow the system to relax to that, so which just will, since this is pointing essentially parallel, that means we'll just hand these local spins a bit away from the axis. Then I change the direction of the field by simply reversing or changing the magnitude of this, changing the amplitude, if you like, from this direction to this direction without changing the angle. So now you see first they will sort of go across here, field reversed, so, and then I wait, and eventually, so you see now these are my end caps schematically, and then I'll be waiting for when I nucleate and the metastable bulk state goes to the stable state. So that's now a sketch of my experiment. Again, these systems, there's a lot of fun you can have here with visualization, and so I've had students who have been interested in that. So this is a field flux line visualization of the pillar, where you can, here, 75 degrees. So now you see that the end cap, rather than sort of being more or less straight across, actually has this rather asymmetric position. This is at finite temperature, and these little undulations here are spin waves. Okay, here is just the detail of the end cap. We had this this got selected for the FISREV V kaleidoscope image gallery back in, I think it was in January, we published this paper. It sort of looks like some sort of exotic flower. Okay, now one fascinating thing about this oblique field thing is that we don't have a single switching time anymore. We actually find that the switching behavior is bimodal. Namely, for this particular 75 degrees, about 60% of our switches happen within 2 nanoseconds. And the remaining 40% take much longer. So what's going on here? Well, in one sense we know, in one sense we don't know. What we have done is looking at paths in the phase space. So here what I'm showing you are two energies. The Zeeman energy, that's simply minus external field times magnetization. And this is the dipolar energy. And we start the system. So let's just look here at the black line. Here is a single round. And we start up here somewhere. So the main change, we have a small, actually, the dipolar energy gets bigger, less negative, but the Zeeman energy gets much smaller. So that's really the driver. So we go through, so here's and basically what I say is that this path goes like this. It slows down a little bit around here, but it keeps going. And that's typically what we see in the fast switches. The path doesn't really, so this is like 100 switches. The black line is one switch. The purple stuff is just a superposition of all the other 60 fast switches. Over here, I have the slow switching, and there, again, I start here, goes there, but then, for some reason that we don't fully understand, the system gets fully trapped in this metastable well. And it just sits there and fluctuates around for a long time before it finally gets itself over the barrier. And then eventually goes to equilibrium.
So the question is, what is that well, or what is the...
Yeah, in what way why does it sometimes fall into this well and other times just sort of skate above it? We have been looking at configurations till we've been blue in the face, and we're not able to see anything clearly different, except that the dynamics really come in these two classes. The ones that just whiz through and slow down a little bit on what's essentially near the top of the free energy barrier, and the ones that get trapped in the metastable minimum and stay there for a very long time.
What are the horizontal lines on the flux?
The horizontal lines here are estimates for the position of the metastable minimum. So essentially the densest part of this black cloud here. And this is an estimate for the top of the free energy barrier, where we're thinking essentially in terms, if I could do this in terms of a single, say chord, like something like this. So this would be the metastable, this is the barrier, and way down here is the stable. And some of our runs then seem to sort of more or less, if I start them here, more or less just jump like that, and the other ones seem to sort of go down, spend a lot of time here before they do that. And we do not fully understand why. Okay, so here's just a movie for this 75. And this, let's see, 50, okay. This is a slow, so it's sitting in the metastable well. And and sitting, and there she blows.
So you would expect the slow one to be the more normal, the more typical situation. The fast, it's a little weird.
Well, it depends. It clearly depends on the angle. Now, these are extremely expensive and time-consuming simulations. So, for this very highest resolution model, we really have only one angle. We have done simulations with a lower resolution where we essentially just represent the system as a stack of spins, so no lateral resolution, and there we have been able, there we can vary the fields and so the angles. So here is just a way of measuring the ratio of the standard deviation to the mean of the lifetime. We can use that as a rough indicator of whether it's a bimodal or unimodal distribution. And so here, so we see that this situation, at least for this lower resolution model, essentially lies as a band close to the coercive edge. And the other thing we see, which is sort of interesting, is that at fields that are very close to the axis, there's some sort of reentrant type behavior of the coercive edge. You can see that more clearly. Here is now my only real comparison with experiments. So these are by Lee and company, that's the von Molnar group. And so this black here is Stoner-Wolfart. So I'm in switching field versus field angle. Stoner-Wolfart predicts this symmetric behavior with a minimum switching field at 45 degrees. Experiments found something quite different with a switching field that's maybe goes down a little bit and then comes up as you increase the angle to 90 degrees. And here is our simulation result. This is again for this stack of spins model. And you see it's certainly much more similar to the experimental results. Then here, this piece here, which has been magnified over here, is this reentrant type behavior that we also know. We know why, and it's in detail in that paper, but I'm not going to go into it now. So, and also I should notice that actually there's no fitting parameters there. All right, so a few conclusions. So single domain, uniaxial magnetic nanoparticles, they're important for magnetic recording, hence there is money to work on them. We can predict the switching behavior with simulations, Monte Carlo and micromagnetic simulations, different aspects of the switching, but we can learn something. We can use nucleation theory to analyze the switching behavior, which puts it squarely in the sandbox of statistical mechanisms. And we showed that we can have this characteristic maximum in coercivity versus field in a strictly single domain particle that doesn't have long-range interactions. Therefore, we don't need explanations in terms of multi-domain equilibrium structures in order to see this. So that we think is a very important point. Also, I sketched some modifications to make our results a little more realistic in terms of system parameters and so on. We really only see quantitative changes. Now, okay, this one is a teaser for tomorrow, when I'll be talking about hysteresis and dynamic phase transitions. So, that's all, folks.
Time for a few questions.
Yes?
Right now it's just one single nanofiller. But in real, you have a lattice of them.
Yeah.
And then there will be this long-range dipole interaction. How will that affect the
system? So essentially, dipole-dipole interaction for parallel spins is ferromagnetic. So that should give a weak ferromagnetic interaction between the different pillars. No. Yeah.
If they're in the plane.
In there. Sorry. It's the other way around. Yeah. Okay. So if they're in the plane, then that should be antiferromagnet.
So if you have one pillar on the top, let's say you have different magnetization. What I'm saying is, on the neighboring pillar, there will be effect from
this, yes, and that would tend. Right, and that would tend to, if the pillars are arranged on the plane, that dipole-dipole interaction would actually tend to encourage neighboring pillars to be oriented opposite. We have done a little bit, but not by far as much as we should, since obviously these are much more expensive, again, simulations. And at the same time, the experimentalists have been able to get down to one single spin, so we met anyway. That's sort of part of the fun in this area, is that at the same time as we as computational theorists have been able to do larger and larger systems, the experimentalists have been able to measure smaller and smaller systems until we are now at a point where we actually can overlap and look at systems of roughly the same size. So that's really why this simulation of nanosystems have had such an explosive growth over the last couple of decades. With, on the one hand, computational resources becoming faster and bigger, and experimental methods becoming more and more highly resolved.
Questions?
Yes?
Yeah, I was just wondering, you mentioned some modifications you made to make this more realistic. I was wondering if you tried to modify the geometry of the nanopillars. I mean, the short corners sometimes are a bit worrisome.
We have done some. I haven't. Mark Novotny has looked some, and it is true, especially like tapering the ends. Actually, you can increase the coercive field, the switching field. I think he actually filed a U.S. patent on that a few years ago. I don't know whether it was granted or not. But yes, that's right. You can definitely do so there. I mean, there's lots of tricks, and this is sort of where it goes from basic science to applied science to engineering and maybe back again. That's why I sort of like to talk about Carnot and that Carnot actually did basic science from the modification of making bigger and better and more efficient steam engines. So it's not that all the inspiration flows from us theorists to the engineers. It goes the other way too. It's a very much a interaction. And I must say, of course, as this becomes more and more of an engineering field, I guess I sort of lose interest a little bit and go to other less developed fields where I don't have to put so many decimals on my answers.